Okay, it's 7 o'clock. We're going to get started. We may have a couple of latecomers, but we have pretty much a full house. It's good to have all of you here. I'm Jerry Schubel, president of the Aquarium. I need to alert you that we have a special person. Not that all of you aren't special, but John Hance from the New York Times is among you, and he is going to want to interview some of you at the break or at the end of the class, and so I hope that you will talk to John. John, do you want to let him know who you are in the back? He's flew in from New York just to be with all of you and participate in this class. So, this is our Aquatic Academy for February, and as you know, Keith, you've got to switch me over here. All right, are we facing an environmental cliff, and if we are, how can we avoid it? Obviously, this is a takeoff on the fiscal cliff, and this is something that we want to explore. And we've got 3 evenings to do it. Some of the cliff warning signs that we'll be looking at in this course are increasing levels of atmospheric CO2, retreating ice around the globe, ocean acidification, and biodiversity loss. Now, extrapolating trends can be a dangerous thing to do unless trends have a lot of inertia, so that's something we will be tracking as we go through these lectures this evening. Other topics we're going to discuss: Californian carbon credits. Is it a courageous move, a meaningless gesture, or is it what the Wall Street Journal described as just another thing in California that will make doing business in our state impossible? And are we kicking the can down the road in terms of climate change? One of the things that this group is going to do, you're going to produce a 10-point action plan that would help us avert an environmental cliff, or what are sometimes called tie-in strategies that even if there's not a cliff, they would be very good things to do. And we're going to try to see if this group of about 40 people can cooperate and come to some consensus and compromise and come up with a 10-point plan. It's going to be published in the Members Currents magazine in the sustainability column. And I'm going to make an arbitrary decision that we have to have 2/3 majority before anything makes it onto this action point of 10 things. And I think we can have some fun doing this. And tonight we're going to hear from Professor Richard Somerville and Professor Eric Rigneau. And after the class, we're going to give you selected reprints from each of our 2 speakers. And I'm going to give you a couple of other thought-provoking articles. There's one particular essay that we're going to give you from Richard Somerville that's entitled, "If I Were President." And it's a very important essay, I think, and it may give some insights in terms of what you want to put on your top 10 list. And you might be thinking in our Q&A of asking each of our speakers what they would put on their list of 10 things we need to do. And having statements like, we need to reduce levels of CO2, that's not a very helpful kind of a comment. So we have to have more specificity. I'm also going to give you a Wall Street Journal article by Bjorn Lomborg. Now, I rarely ever agree with what he writes, but it's interesting, there were a couple of things in his article that come close to Richard Somerville's "If I Were President, what would I do?" Because you have to do things that are going to make a difference. Andy Revkin, journalist with the New York Times, wrote on his blog about a year ago that the 2 phrases that characterized the environmental movement in the last century were, "Woe is me," and "Shame on you." And he pointed out that he too had been guilty of those 2 phrases, but he cautioned that in this century, we have to get beyond "woe is me" and "shame on you." We have to be thinking very boldly about what we need to do to ensure this future. So we do want to come up with the 10-point program. It will be your 10-point program. And as I say, we're going to put it in our Members magazine. Now, I'm personally convinced that it is not too late to avoid the cliff. if there is a cliff. Our children and grandchildren will live in a different world than the one many of us grew up in. It'll be a warmer world. There will be a higher sea level. But in many ways, I think it can be a more just, a more equitable world. And while we have fundamentally altered the two global commons, the atmosphere and the oceans, there now is a third global commons that should give us hope: the information commons. Because for the first time in the history of humankind, we can actually share data and information in real time, and we can increase the opportunities for collaboration, for innovation, and for problem solving. And I think the only way we deal with these issues, if we can create a global community that's made up of local and regional initiatives of people who share concerns, hopes, and dreams of a different kind of a world. And certainly opportunities and education and population go very much hand in hand. And if we're going to slow down the rate of population growth, it will require education and opportunities for women. So we're going to explore all of those. I'm not going to give you bios because they're all, each of you has brief bios of all of our speakers. I will put a plug in for Richard Somerville's book, The Forgiving Air. If you've never read this, it's one of the best books, I think, for general audiences like ours to get your arms around some of these big issues. So tonight we're going to start with Richard Somerville, and then Richard will talk for about 45 minutes. We'll have 10 minutes or so for Q&A, and then we will take a short break, and then Professor Eric Rignot will talk about ice and retreating ice. So Richard, we're all ready for you. Please join me in welcoming Richard Somerville.
Okay, thank you all for coming. It's a privilege to be here. I've spoken at the Aquarium before. I've always had a wonderful time. And how do I start these? Okay. The thing to notice on this slide here is my website. I really encourage you to explore it. It has a lot of links and downloads. It's got a lot more information. It's directions and to sources of good information. I'm at Scripps Institution of Oceanography at UCSD, and I want to introduce you to a true scientific hero. This is Charles David Keeling, who spent his entire career at Scripps. I knew him very well for the last 25 years of his life, and it's to Keeling that we owe the knowledge that carbon dioxide is increasing in the atmosphere, and that's because of human causes. He spent his life doing this. He came to Scripps in the 1950s as a postdoc in his late 20s. A postdoctoral fellow is the lowest form of life on the academic totem pole, but he very quickly made his mark. He invented the instrument that measures carbon dioxide. There was no accurate way to measure carbon dioxide before he invented this instrument, and he spent his life improving it and using it to monitor carbon dioxide. He's one of the most long-term stations. The longest record that he established is on Mauna Loa, partway up on a volcano in the Hawaiian Islands. And Keeling set up his instrument there in 1958, so you can see he was about 30. All those pictures of Einstein, the white-haired guy, are long after he did the good physics. People do their good physics often when they're very young. And Einstein did, and so did Keeling did his great work. Starting in 1958, he measured the amount of carbon dioxide in the atmosphere. You can see the first few years of record down there in the lower right. And that curve has been extended. It's being carried on by scientists all over the world, including Keeling's son, Ralph Keeling, who's also a professor at Scripps now. And this is accurate up to a few weeks ago. And you can see that in these units, which are equivalent to the number of molecules of carbon dioxide per million molecules of air, the number was 314 when Keeling began in 1958. It's about 395 today. The upward trend is entirely human-caused. There are no natural reasons why it's higher today than before. Keeling established that fact as well. And you can see 314 then, 390 odd today. It's an increase of about 20% in the time that this curve extends over. We know what the amount of carbon dioxide in the atmosphere was long before now, although Keeling wasn't measuring it. Air has been trapped in ice in Greenland and Antarctica, and the ice can be cored and dated, and the tiny bubbles of air trapped in the ice analyzed. And in the late 1800s, before human activities began to significantly increase CO2, the number in these units was around 280. So it's gone up very significantly. And the ups and downs are the interaction between the atmosphere and the world of living things, especially plants. It's the biosphere breathing, if you like. And so the amount of carbon dioxide in the atmosphere is drawn down in northern hemisphere spring. It's in the northern hemisphere largely because that's where most of the land, hence most of the plants are. And as the photosynthesis converts that carbon dioxide to tree material, and in the fall, when the leaves fall off, the trees respire, and the CO2 is returned to the atmosphere. You can see this is not a straight line. If you kind of mentally filter out the annual wiggles, you can see that it's rising more rapidly now than it was at the beginning, and there were some ups and downs. And the data are so good, Keeling said at one time that he made the instrument 10 times more accurate than he thought it needed to be, just because he had figured out how. And so you can see El Niños, you can see the Arab oil embargoes, you can see all kinds of things. This data has been a treasure trove, and it's surely the most important record and the most famous graph in all of Earth science. So CO2 is going up. It's going up because of human causes. And the main cause is burning coal and oil and natural gas, and there are secondary causes, including land use changes such as deforestation. And Keeling established that too. At the same time, temperature has been going up. And you're looking here at the world's average temperature, the atmosphere just a little bit above the surface of the Earth, from the middle 1800s up until today. The two curves shown on here, labeled Hadley and Gist, that's two centers, one in England and one in the US, that keep track of these data. It's not a straightforward job because the data have to be corrected for instrument changes and many other factors that can lead to errors in the data. And you can see the two curves that occasionally differed substantially from one another in the distant past. They're much more on top of one another today as the data coverage has improved. You're looking at both the annual year-to-year variations, that's the sharp jagged lines, and the smoothed curves, that's the more solid, gently oscillating lines. And those ups and downs are caused by natural factors, such as El Niños and volcanoes. And I'll say more about this record later on, but there are several places around the world where scientists analyze the data from the surface of the Earth, and these records lie on top of one another. There's not much doubt that the Earth has been warming. It's warmed, this is labeled in Celsius, it's warmed about 0.8 of a degree Celsius since the 1800s. That's 1.4 degrees Fahrenheit, approximately. And may not seem a lot. People say I moved from Denver to Long Beach, and the temperature change went up by a lot more than 1.4 degrees Fahrenheit, and I kind of like it here. But 1.4 degrees in terms of the planetary average temperature is a significant difference. The difference between ice ages and interglacial periods like today is only a few degrees. We'll say much more about this later on. A lot of things have changed besides the surface temperature of the atmosphere near the surface of the ocean, and here are some of them. White means things are increasing, and black, which refers here to ice and snow, are decreasing. And all of these things are being monitored, and in some cases monitored by novel and fascinating instrument systems. For example, ocean heat content, that white arrow at the lower left, is being measured today by an array of about 3,000 floats that are programmed to monitor the deep ocean. They pop to the surface at regular times and transmit data to satellites and then sink back to the preassigned depth. And sea level is measured largely from satellites today. And we'll talk about some of these as we go along. But the point is that the world is definitely warming, and we don't know that just because of one data set, but because of many, many measures, of which here are 10 important ones. This picture here is a striking result, which was a surprise. You're looking here in this sort of yellowish color, the average extent of Arctic sea ice at the time of the annual minimum, which is around September. And in the yellow, it's an average for years from the beginning of the satellite era in the late 70s up until 2006. But in 2007, there was a surprising dip in the ice amount that hadn't been forecast. That was, I think, a surprise. The next speaker, Eric Vigneault, is going to talk a lot about ice, and so I'm not going to. It's not my specialty, it's his. But I wanted to mention this as, you might say, a way to set the stage. I'm showing results, by the way, from a number of assessments of climate science results. That is, there have been a number of bodies of scientists who have gone over the published scientific research literature, the things that scientists write results of their research in, it's peer-reviewed, and they've assessed the state of the science. That is, they've used expert judgment to try to decide what things we know, why we know them, what things we know less well, where the research frontier is, which are the open questions. And these assessments come out regularly, and all the slides that I'm showing you tonight are from 3 assessments. One, the last report of the Intergovernmental Panel on Climate Change, an international body under UN auspices that does this every 6 years or so. That came out in 2007. Second, figures, including this one, are from a report came out 2 years later, 2009, called the Copenhagen Diagnosis, which was a report by a smaller group of scientists put out in a hurry with less thorough review, but more up to date, intended to update the results of the IPCC report. And the final assessment on which I've drawn is a draft version of the United States National Climate Assessment, which is an ongoing report, a draft of which is now up on the web for public comment. I'm an author of all 3 of those reports, and so I'm not speaking for any of the reports officially, only for myself, but I think the results that I'm showing you tonight are, you might say, mainstream climate science. They're not controversial, and they're taken from, you might say, the state-of-the-art best expert judgment assessments. This picture here, also from the Copenhagen Diagnosis, shows the fall in the aerial extent of Arctic sea ice at the annual minimum around September. The red line is the observations, and the blue area with the black line in the middle is the range of forecasts of Arctic sea ice extents that have been in the scientific literature prior to this time. So you can see the especially low Arctic sea ice extent in 2007 fell well below the range of what expert judgment was as to what Arctic sea ice was likely to be. I'll say more about that later on, and you'll hear a great deal more about it, I'm guessing, in the second talk. Anyway, this was a surprise. What I'm trying to say is that we make projections as to how the climate will change under given assumptions, and sometimes they're accurate and sometimes we get surprised. This was a surprise. You're looking here at what sea level change was over the period from beginning in 1970 up till near the present, actually till 2010. And this graph is an update of a paper by several authors, I'm one, that came out in 2007 at the same time as the last IPCC report was released. And sea level change, it doesn't change by large amounts. This is the global average sea level. And as you can see, it's a few centimeters. 2.5 centimeters makes 1 inch. So it's only gone up a few inches over this time. 0 is an arbitrary average sea level for this period. And tide gauges, the red line at the lower left, refers to the practice of measuring sea level by devices that are basically simple floats that are placed on shorelines, at the end of piers, for example. And there's a global network of these. But in a modern development is satellite altimetry. You can measure the distance from the satellite to the ocean, and you can monitor sea level from the satellite, which gives you global coverage. And you can see that the satellite observations in the blue fall on top of the red line there, but more detail. That falls near the top of the range of forecasts that had been made. That's the gray area there, a range of projections as to how much sea level could be expected to rise under given assumptions. So Arctic sea ice extent has decreased more quickly than had been expected, and sea level has been rising near the top of the range. Sea level rise is an expected consequence of a warming world for two main reasons. One is that the ocean, like many other things, expands as it gets warm, takes up more volume. And the other is that ice on land in a warming world melts, and much of that water eventually finds its way to the ocean. So the amount of water is also increasing. And sea level rise can be very large. The sea level difference between an ice age and a present day, for example, can be in the neighborhood of 100 meters, several hundred feet. So sea level rise is happening. The interesting question is how fast it will happen. By the way, these are average numbers over the whole world. Sea level rise at any particular location is more complicated. For example, the land itself can be rising or falling. The IPCC is a 1,000-page report for the physical science of climate change. And for congressional staff, that's compressed into a 30-page summary for policymakers, and for the press, no insult intended to the press, that's compressed into 2 key sentences. And here's the 2 key sentences from that report. Warming of the climate system is unequivocal, and there are many chains of evidence. It's not some slender thread of evidence, but there's many, many reasons for saying that the climate is warming. There isn't any doubt about that. Here on one graph is the average of the Keeling curve, the CO2 amount. Concentration is jargon for the total amount of CO2 in the atmosphere. And the annual wiggles here have been smoothed out. And the legend is over there on the right. You can still see the numbers from a little bit below 300 back in the 1800s on the left, up to approaching 400 today on the right. And the bars are the annual average temperature of the atmosphere near the surface of the Earth. Each bar is a year, and the line in the middle is just the average temperature for this period. And you can see that it was colder than average for many years up until about 1940, and then there were some years above and some years below until the 1970s, and since then it's all red. All the years have been warmer, and it doesn't warm evenly. That is, each year is not necessarily warmer than the year before, and again, that's because of the factors I mentioned that make one year different from another because of naturally varying things like coming and going of El Niños and occasional volcanic eruptions that temporarily cool the world. So the world has been warming and CO2 has been going up, but that by itself is just correlation. It doesn't necessarily imply causality. A lot of other things went up over that period too, population and the stock exchange and hemlines and many other things. The question of whether there's a cause and effect here is an interesting issue to which a great deal of scientific attention has been devoted. And here's the bottom line. I'll tell you where this result comes from, but this is the quote from the IPCC. This, by the way, is the language that's been approved word by governments in a little mini UN General Assembly. So no matter where you're from, every government in the world, including yours, has agreed to every word in this statement. It says most, that means more than half, of the observed increase in temperatures since the middle of the last century is very likely, and down there in parentheses it says that's IPCC calibrated language, meaning chances are at least 9 out of 10 that it's thought to be true, is very likely caused by the increase in anthropogenic greenhouse gas concentrations, which is jargon for human-caused heat-trapping gas amounts. So carbon dioxide and other heat-trapping gases, of which carbon dioxide is the most important one under human control, has been rising and strengthening the natural greenhouse effect, and the result is the most of the observed warming in expert judgment. There's an IPCC website there at which you can read all of these reports and many, many other things. The question of how we know that is not simple. And part of it is in this picture here. What you're looking at here in these figures, there's 9 figures here. The bottom left is the global average. The bottom center is the average of all the land on Earth. And the bottom right is all the ocean on Earth. You're showing in black on each of these figures, and the 6 figures above are on the 6 inhabited continents. You're showing the record of temperature. So in all of them, you can see the world is warming. That is, recent years, the right-hand half of the figure, in every picture there show an average warming. That in itself tells you a lot. So for example, the bottom right says that the global ocean has been warming in recent decades. That tells you right away, for example, that the warming is not due to cities. There aren't any cities in the middle of the ocean. So the ocean, lacking all urban influences, is warming. And so are all the continents. And the pink and the blue areas there are the results of computer simulations. We make a computer model that synthesizes what we understand about factors that can change climate. And we run it under two sets of assumptions. The blue, only the assumption that only natural factors are at work. The sun can change and so on. And the pink, in addition to that, the human factors, the increase in greenhouse gases like carbon dioxide, the increase in small particles in the atmosphere, can also be allowed for. And it's an area rather than a line because there's lots of different computer models. And so the pink area with the human factors is, as you can see, the only one capable of replicating the observed warming. The blue, when we only allow the computer to take into account natural factors, doesn't show the recent warming. That's part of the evidence for the human cause of the observed warming. There's many other aspects of it too, and there's a whole branch of climate science called detection and attribution. Detection means establishing that something unusual is happening, and attribution means assigning it a specific cause. So for example, you can say, it's a perfectly reasonable question, well, wait a second, can't the sun change? And can't that change climate? The answer is yes, it can, and yes, it has. But we can measure now how much the energy from the sun changes over, say, the 11-year sunspot cycle. And it's 0.1%. And if you convert that to a unit comparable to the effects of carbon dioxide, it's much smaller. So the sun hasn't changed enough to matter. How about long-term trends in sunlight? And you can do that too. You can evaluate them. And in fact, the sun has been gradually cooling. If it were the only factor, we would have expected to see a cooling climate. And you can do that with all the plausible aspects of the climate system, which is complex, and come up with the conclusion that we can't account for the observed warming in recent decades without attributing it largely to human causes. This is the most important graph that I'm going to show, or rather this is the one that has the main take-home message for you. It came from the Copenhagen diagnosis. And what you're looking at here is, on the left-hand side, recent years, 2005 on the left, 2010 when this came out is the dashed vertical line, and over at the right, mid-century, 2050. And you can see three lines on here, a green line in which what's being plotted here is the rate at which we emit carbon dioxide in billions of tons. GT is geek speak for gigatons, or billions of tons. And so the green line says, this is what might happen if you peaked the emissions at 2011. They've been going up pretty much every year after year, and then let them gradually decline. The blue line is if you peak them 4 years later, 2015, midway in the current decade, and then they decrease more rapidly. And the red line says you peak them in 2020, and then they reach zero before mid-century. And what each of these lines has in common is that they are all possible pathways that give a 2 out of 3 chance of limiting global warming to 2 degrees Celsius, an arbitrary number, which is 3.6 Fahrenheit, above what the average temperature was in the 1800s before the industrial processes began putting large amounts of CO2 into the air. In other words, we're saying now, suppose you decided, you king of the world, decided that a tolerable amount of global warming was 2 degrees Celsius, or 3.6 Fahrenheit above the 1800s. That's a subjective judgment. That might depend on your values, your priorities, your tolerance for risk. But after all, you can say there's some amount of warming that I think the world could adapt to. And I, as king of the universe, want to take steps to limit the warming to that amount. If you said that, and that's, again, not a science judgment, that's a political judgment, if you will, the science can then say, all right, if that's your goal, then we can't give you any guarantees, but you'll have a 2 out of 3 chance of keeping the warming to within those limits if you have only a certain amount of carbon dioxide in the atmosphere. That's an interesting result. It's a very simple result to state that comes from a lot of complex science. So take my word for it that to a very good approximation, the amount of warming the world will experience is due to, depends on, the total amount of heat-trapping gases, of which CO2 is the most important human-caused one, in the atmosphere. And that's for several reasons, one of which is that the stuff stays in the atmosphere a long time. The carbon dioxide that you put in the atmosphere today because you drove your car, which turned gasoline into lots of things, including CO2 that came out of the tailpipe, or that the electric plant that supplies you produced, that carbon dioxide, it's complicated. Some of it leaves the atmosphere fairly quickly, goes into trees, some of it goes into the ocean, but much of it stays in the atmosphere for centuries. That's just a natural result. That has many consequences. One is that the wind has plenty of time to homogenize the atmosphere, to blow that CO2 around and equalize the concentration. So the CO2 over Long Beach, for example, is not due to what the good citizens of Long Beach did or didn't do. It's due to the total amount of CO2 in the whole world. Locally, sure, cities are a little bit higher, but for climate purposes, the CO2 amount is the same everywhere, very nearly the same. Keeling knew that. That's because he had actually, before he started these measurements, tried it out in different places and got the same reading. And so he realized that if he put his instrument at one pristine location, middle of a Pacific Ocean, the top of a mountain, he'd get a reading that was representative of the whole world. I said that he came to Scripps as a callow postdoctoral fellow, and I'll tell you a true story. He had an argument with the director of Scripps who had hired him, who was a towering, charismatic, commanding figure named Roger Revelle. And Revelle said, "Welcome, young man, you're at Scripps now, you're an oceanographer, I'll tell you what we're going to do. We're going to put your instrument on a ship, we're going to cruise it around the world, we'll make measurements everywhere, and we'll go back in 10 years and repeat the measurements and see if they've changed." And Keeling, a very green guy, said, "That's a real stupid idea." And he explained that CO2 stays there a long time, and if you measured it accurately in one location, continually, you'd get a record that was representative of the whole world. And he was proven right. So I tell young postdocs, don't be afraid to tell your boss that he's stupid if you're dead sure. So this is an interesting graph because what we've said here is that if the world wanted to limit things to 2 degrees Celsius, you have a choice. There's only a certain amount of CO2 you can have in the atmosphere. And that's actually the area under this curve extended way back. It depends on the cumulative emissions because it lasts so long. And so all these three curves, and any number of others you could draw, have the same area very nearly. And so if you were able to start emissions reductions last year so that the global emissions started to go down, you could afford to let them coast down at 3 or 4% per year, whereas if you waited until 2015, they'd have to go down much more rapidly, or they'd exceed the amount compatible with 2 degrees. And if you wait till the end of the decade, you have the problem of having to decrease them at a rate almost 10%, which economists will tell you might be impossible. And that's why I put urgency in the title of this talk. Mitigating climate change is not like a lot of other things you'd like to do. You might like to negotiate better steel tariffs, for example. If you don't get it done this decade, maybe you'll get it done next decade. But for climate, if you want to limit the amount of global warming to a level that's been widely agreed to be roughly what's tolerable, you can't keep waiting. The world has been procrastinating for decades. These results were essentially known in the 1970s. And the world has continued to increase emissions. It's in the position of an obese person who should be dieting, but instead is taking in more calories every year. And so if you don't get it done within the next few years, not 50 or 100 years, but 5 or 10 years, then you are essentially sentencing our descendants to dealing with a climate in which the climate change has been more severe than it would be at 2 degrees. Nothing magical about 2 degrees. I tell people it's like a cholesterol number. You know, there's no cholesterol number your physician can tell you above which you're going to have a heart attack, below which you're guaranteed to be safe, but the risk goes up as the number goes up. And this says that in words. I've been taking courses on how to speak effectively, and I don't put big wordy slides, and here's the exception. The decision is a subjective judgment by governments. And in fact, a lot of governments have signed on to it. The European Union, which has more people and a larger gross domestic product than the United States, has taken it as an official policy position. It's an official policy goal of the European Union. And many other governments have signed on to it as, you might say, an aspirational goal, including the US. But once that decision is made, then science comes to your rescue. In the same way that once you've decided what your weight should be, medicine and nutrition and lots of other sciences come to your rescue. And science says that the global emissions have to be reduced and you have to do it fast. So the urgency, given this target, isn't ideological. There aren't any Republican or Democratic satellites or liberal or conservative thermometers. It's scientific. The climate science says you can't just wait forever. So that's the message, and the rest is elaborating on it. Do you know the story about the doubter who told the rabbi, "I'll believe this hocus pocus if you can explain Judaism to me while standing on one foot"? And the rabbi lifted one foot and said, "Do unto others as you would have them do unto you. Now go and study. The rest is commentary." So I have some commentary, but that's the result that I wanted you to take home. These are from the National Climate Assessment Draft, which is out for public commentary now. And what you're looking at here is several scenarios. And they have god-awful names. These A2, A1, B, B1s were set up by IPCC, and these scenarios here, with RCP in front of them, recommended concentration profile or something like that, were set up by the National Climate Assessment. And the RCP 2.6 is pretty much like the blue curve, this curve here. It's a rapid reduction in emissions coming to zero near zero by near mid-century. I call this, by the way, the ski slope diagram. You see, this is the bunny slope, this is the intermediate slope, this is the double black diamond expert slope. So RCP 2.6, the lowest one here, is one in which actions have been taken to reduce emissions rapidly. And what you're looking at here is as a measure of climate. Climate's complicated. Climate is extremes as well as averages. Climate is severe weather and droughts and all the rest of it. But a symptom for climate is this global average temperature change, just the way the symptom for a disease is a fever. And this says that if you start soon, then you can stabilize the warming at around 3 Fahrenheit, which is a little under that 2 Celsius. But it requires rapid reduction. And anything less rapid, including these business as usual scenarios in red here, where emissions keep increasing, leads you to more severe warming. We're on roughly the trajectory of A2 here, or RCP 8.5. That's just extrapolating current trends, which mean people keep having babies and the world keeps running on 80+% fossil fuel energy. Okay. Here are some pictures of the world as it might differ. On the left is the warming. The key down here is in Fahrenheit degrees with 7 or 8 degrees in the middle. Under a low pathway, RCP 2.6, the intermediate slope on the ski slope diagram. And here is the world on business as usual. This all takes some explanation. I'm going to be able to give some details in the time allowed. These are the temperature changes in 2071 to 2099, essentially the last 3 decades of the current century compared to 1971 to 2000. So the last 3 decades of the 21st century compared to the last 3 decades of the 20th century. You can see the warming is greatest over continents and over ocean, for much the same reason that your toes get burned on the beach on a hot summer day, but not in the water. And the strongest warming, as you can see, is in the Arctic, and this is due to feedback processes. The complicated stuff about climate science is changes that cause other changes. And in the Arctic, for example, one such process is that ice and snow melt. You saw Arctic summer sea ice melting, and revealing darker water under the sea ice or darker land under the snow on land, and that's more absorbent. Dark absorbs, light reflects. So warming the world darkens the Arctic, which increases absorption of sunlight, which adds to the warming. That's a feedback that's a vicious circle. And so the strongest warming, generally speaking, is in high northern latitudes. But you can see that this is a warmer planet. These numbers are here in the range 1 to 3 Fahrenheit, except in the Arctic. This is a different world. This is precipitation, and as it says here, wet parts get wetter and dry parts get drier. Here again, you're looking at the last 3 decades of the current century, in this case compared to 1901 to 1960 globally. So you can see that on the low pathway, places like the tropics, where heavy thunderstorms happen all the time, get even more wetter, and dry areas, these light tan brown colors, get drier. Here it's exaggerated. This is on the low emissions pathway, the intermediate slope on the ski slope diagram. This is on business as usual. And you can see here that the dry areas get a great deal drier. So this dry area here extends from the Sahara across low tropical latitudes of the North Atlantic into Central America and the American Southwest. In general, it gets wetter in the northern part of the United States and drier than the southwestern part, and that's complicated. For example, one of the things that happens is that storm tracks, the paths that migratory cyclones follow across the continent, move toward the pole. They move north of the northern hemisphere. And the reasons for that are complicated. So these are the results of computer simulations, but many of the results that we've been seeing are mimicked in the observations. We're seeing what the computer models have been telling us to expect. This is the United States. It gets much warmer in the heart of the country under the high emission scenario. I'm going to speed up so that I don't run out of time here. And this is, I told you there was a second surprise in Arctic sea ice. So what you're looking at here is the sea ice cover again in time of the annual minimum near September last year. And here it is down here on this graph where this was the previously unprecedented 2007 result, and now it's gone even further down. So there's been a very rapid decline, and in recent years a couple of exceptionally low sea ice coverage. This is sea ice extent. This is the aerial coverage, what's easy to map from a satellite. At the same time, the ice, much of the ice has been getting thinner, so the volume, the thickness of the ice times the aerial extent has been decreasing more rapidly still. This is projections from computer models, again following these scenarios, again this from the forthcoming US National Climate Assessment Report. And you can see that under the business as usual scenarios, the highest emissions of heat trapping gases, that's here, this red line as the mean, the pink area is the range, the sea ice essentially disappears well before end of the current century. Whereas if you stick to the rapid emissions reduction scenarios, RCP 2.6, the greatest one, then you halt much of the decline a few decades from now. I'm putting this in for perspective. This is sometimes called the hockey stick diagram. This is 300 AD, or 300 of the Common Era, and the present on the right. And this is the temperature, average temperature over that period from proxy data. There weren't any thermometers to speak of long ago, so this is temperatures inferred from substitute data like tree rings. And the red line here is the instrumental record. There's a period here called the medieval warm period. It wasn't necessarily warm globally average, but it was warm in parts of Europe. And here the Little Ice Age. And this cooling trend stopped, though, after human emissions of heat-trapping gases became strong. So it's warmer now than it has been in at least the last 1,700 years. I stuck this in to give me a chance to attack a prevalent myth. You will hear some skeptics or people who are unpersuaded by mainstream climate science say, there isn't any more warming. Global warming stopped in 1998, which isn't true. It just isn't true. It's cherry picking to say I'm going to take 1998 as my starting point and measure temperatures since then because, as I said 2 times earlier, temperatures go up all the time. 1998 was a big El Nino year. These low points here tend to be La Nina years, where heat temporarily goes into, for El Nino, and out of the atmosphere. And there's enough natural variation year to year that each of these blue lines here, which is a 5-year average, can point any which way you want. This one's slightly cooling, this one's rapidly warming, cooling, warming, cooling, cooling, warming, cooling. So the way to measure a long-term trend is to take a long-term data set. And when you do that, it's clearly warming all the time. The minimum length science establishes for a long-term trend of a variable like average temperature is probably 20 years or so. This is the period from 1970 till 2010, much more than that. The temperature is rising if you smooth out these interannual variations, which you should, at a rate of about 1/3 of a degree Fahrenheit per decade, which is what the models have predicted. Another way to look at the same story is to look at this. These are decadal averages. So the decadal average global temperature has been plotted as a bar for a decade. Mind you, the data are not as good in the late 1800s and early 1900s. But the warming we're talking about started in earnest in the 1970s. We think, we're not sure. I've tried to pick topics here that we're pretty certain about. But one thing we're not sure about is why the warming seems to have paused from roughly World War II into the 70s. And the most prevalent opinion is the atmosphere may have been dirty then. The Clean Air Act and similar laws in other countries hadn't been passed. And so the prevalence of strongly reflecting particles in the atmosphere, pollution basically, may have masked global warming. When the atmosphere got cleaned up, the warming showed up. And you can see here, in the 1980s, that was the warmest decade on record globally at that time. But in the 1990s, every single year in that decade was warmer than this average. And even with the ups and downs due to the natural causes. And in the 2000s, the first decade of the current century, every single year has been warmer than the average for the 1990s, which you could read off this chart here too, but that I think dramatizes it. And here's why. Emissions are growing enormously. And all the fossil fuels, which together comprise roughly 80-odd% of the global energy source, are increasing. There was actually a kind of one-year blip due to the global recession, but growth has resumed again. And this causes geopolitical difficulties too, because the fact that there's so much carbon dioxide in the atmosphere is largely due to the industrial West, which was putting it in while the developing world was not yet doing that. Today, China has passed the US a few years ago as the largest net emitter of CO2. But, so you see a lot of finger pointing. You caused the problem. You're making it worse. No, it's not very useful, but it's true. There's much that can be done, and I want to close with a couple of statements about that. This is based on work by several scientists who speak about wedges, that is to say, steps that could be taken that would slow down the rate of growth. There are quite a few of them, and you can see them labeled here. More efficient electric use, more efficiency in other sectors, higher miles per gallon standards for cars, same for trucks, planes, and so on. I think the way to look at this is to say, as far as we know, there's no silver bullet. There's no one thing you could do if you were a well-intentioned political leader to reduce global emissions of heat-trapping gases. No silver bullet has shown up. You can't predict a breakthrough, maybe it will happen, but there is silver buckshot. There are things that you can do lots of, each of which does a little bit. And this is an example of that. And there's a great deal of thoughtful, careful, analytical work that's been done about this that I'm not going to have time to talk about, but I think there's reasons to be hopeful. This is from the Union of Concerned Scientists and is reproduced in this National Climate Assessment. And it's a restating of two possible pathways. So the way to look at this is that the blue line says that to achieve a reduction of about 80% below 2000 level of emissions globally, and to get it done by mid-century, by 2050, which is what you need to do to stabilize the concentrations at the level that gives you a reasonable chance of limiting warming to the 2-degree target. You can start in 2010, that's the blue line, and cut it 4% per year, or you can wait till 2020, and then you have to cut it by 8% per year. It's a restating of the ski slope diagram. There's many ways to say this. I wanted to have one clarification of terminology here, and that's why I put this slide here in, because think of concentration as the amount of CO2 in the atmosphere, or the amount of water in a bathtub, and emissions the rate at which you're adding to it. So when we say concentration, that's what Keeling was measuring, the amount of CO2. That's the bottom curve here. And what you want to do is stop the increase in concentration. The red line is business as usual, and then stabilizing it. But if all you did was to stabilize emissions at present day levels, you're still putting more CO2 into the atmosphere than natural processes are taking out. So the concentration's going up, just at a slightly slower rate than if you let emissions rise. In order to stabilize concentrations, which is what you need to stabilize the climate, emissions must decrease. And when you run the numbers, as I've said several times now, you're looking at a reduction, not of a little bit, tinkering at the edges doesn't much help, but really weaning the world from fossil fuels, or doing the equivalent. And you get to do that only if you are willing to do draconian emissions cuts by many different methods, like the buckshot diagram showed. So keep that in mind. You want to reduce emissions significantly, that's the top figure, in order to stabilize concentrations and hence stabilize the climate. I put this up here just to sear it into your cerebral consciousness. I want to close on a happy note, or an optimistic note. I'm a technological optimist. I think a lot can be done. Politically, I waver and worry. But I think if you look back as to what has been behind many of the great transformations in our world, in our lifetime, think of the influence of a Nelson Mandela on apartheid, or of a Martin Luther King on civil rights, or of a Gandhi on Indian independence, or pacifist leanings generally. And I think when people of great moral authority and widely respected people take up these causes, things happen. And I'm encouraged by the degree to which people like that are beginning to take an active role in saying that this is an ethical and moral imperative. It needs doing. And this picture here is very, very moving to me personally. My colleague at Scripps, Ramanathan, who's a climate scientist, and I spent a day with the Dalai Lama, who was touring and came to San Diego and talked about climate change this entire morning. The stuff is online, and I urge you to go and look at it. When people of that stature, you don't have to be a Tibetan Buddhist to have respect for this man. When people of that stature say that this is important, I get optimistic about what can be done. Well, I was told to finish in 45 minutes or I would be thrown to the sharks. Thank you.
Thank you. Before we take questions from the audience, I want to remind people, I'm not sure you fully understand, you are in the presence of three of the world's greatest living climate scientists this evening. Richard, Eric, and Katerina. There aren't any better climate scientists. And it's unusual that you would have three of them in one room with you, so I hope you really appreciate that. We have a few minutes for questions or comments for Richard. Yes, go ahead.
One of the last graphs was about the carbon dioxide. What would be considered a reasonable, a level that we need to sustain? I saw the graph was going all the way up to 900 ppm.
Yeah. There's uncertainty, and that's why these graphs are labeled to give you a 2 out of 3 chance of making that and so on, because it's tricky and other things matter, and we're not exactly certain of how fast processes happen. But if you want to pick a round number to aim for, Bill McKibben has done it, 350. 350 parts per million would give you a good shot. Part of the problem is that there are other heat-trapping gases that I haven't mentioned. CO2 is the most important one. And so when you start converting them to their equivalents, you're doing your best at what's an apples and oranges comparison. So let me repeat the question, because this is being webcast and recorded. The question was, what would be a safe level of CO2? And I think if you have to pick a number, 350 parts per million.
What are your views on, as the temperature rises and the peat moss melts and the other gases, greenhouse gases go up, which are worse than carbon dioxide. Where do you see that playing into this?
So the question was,
Methanes and such.
question is what happens if things like methane emerge from the soil or from the ocean as the temperature rises? And I said at the beginning that I was going to try to restrict myself to relatively well understood things, solid results, things you can hang your hat on. But that's a serious possibility. That comes under the category of tipping points or nonlinearities or thresholds or places where you can flip things and they don't flip back. Where you a little bit more push, it's like the old-fashioned spring-loaded light switch. You push it and push it and push it, and then at some point you push it a hair more and it clicks over into the other position. And so we know that there are tipping points like that in the climate system. And we're pretty sure that there are some unknown unknowns, that there are tipping points we don't know about. And they're inherently unpredictable. You can't say there's a particular amount of warming that will trigger one of those. You can only say that the risk goes up. And I think some of the results that I've shown you today, showing, for example, Arctic sea ice extent at the summer minimum decreasing more rapidly than expected, or sea level rising at the high end of projections, are a hint that these things are there. And when in melodramatic demonstrations, I put a glass of water on a black tablecloth and close my eyes and push it towards the edge. You see, you don't know exactly where the edge is. So I think Jerry's metaphor of a cliff is very apt in some sense. There are surprises there. We know from paleoclimatic evidence looking at distant past that the climate has changed rapidly in short amounts of time. And so it's a question of how lucky do you feel?
With your essay, If I Were President,
Yeah.
you've just been reelected as president, you've got 4 years left. What are 5 things you would push on in the second term?
I thought this was a friendly audience. The essay, you're going to hand out the essay, and it's on the website. You know, in all seriousness, there's a limit to what a president can do, but he has a bully pulpit. And I sometimes think that a president, and Obama made a good step in that direction in his second inaugural address, if he stood there and said, this is important. You know, we didn't seek control over the climate of our children and grandchildren, but we've got it. And we have to decide what we're going to do about it, and doing nothing is a serious decision. This is important to the security of the United States, the prosperity and economic competitiveness, and it's important to the planet. And then use the power of the president to do lots of things by executive decision, which he has done some of in the first term. And furthermore, I think, play a leading role in the world. The United States is perceived as a foot dragger on the international stage here. It's been unwilling to make commitments. The Kyoto Protocol, which everybody knows was a tentative step, wouldn't have solved the problem, but kept it on the table, kept it under discussion, paved the way for later more serious reductions. The U.S. just unilaterally declared we're not going to sign that. It doesn't put limits on China and India. Don't even bother asking. It was a unanimous Senate decision, essentially. So I think if the U.S. would say this is important to us, look at the problems that have been solved in the past that were large. Transboundary air pollution, for example, the pollution put in by one country that acidifies lakes of a downwind country. Or look at the decision to, in the Montreal Protocol and subsequent treaties, to eliminate the production of man-made substances that cause the loss of ozone in the stratosphere. I mean, those started small, and the U.S. took leading roles, and money changed hands, and technology changed hands. The biggest and strongest country in the world can do a lot. And so I'm optimistic. I think it just requires political will, you might say, which comes from people telling their politicians that this is important to them. So
there's another point that you made over dinner that I want you to restate. We often hear, with those of us who are involved in aquariums, that the children are our future. Mm-hmm. And yet all of the data suggests that it would be people, the age of the people here, who will determine what kind of a future our children and grandchildren live in. Yeah. We ought to be paying attention. Yeah, I think that's, there's a lot of truth to that. You know, there's an organization that started out with the scientists from the Manhattan Project, the people who developed the first atomic weapons, who formed a group called Bulletin of the Atomic Scientists and established a kind of iconic thing called the Doomsday Clock, which they every year set a little bit closer or further from midnight, as a measure of their judgment as to how much civilization is at risk from
nuclear catastrophe. And recently they've added other factors, and climate change is one of them. And so I think it's a good sign where serious people are thinking about it seriously. But I'm here to talk about urgency. I mean, I put urgency in the title. I showed the ski slope diagram twice. You've got to get off the dime. You just can't stop being silent about this and watching emissions go up year after year. This is a time when I think our descendants won't look kindly on us if we fail to act.
And Katerina has an answer with her new organization. Do you want to put a plug in for your new organization?
Oh, thank you. Yeah, we're thinking about the Union of Concerned Grandmothers, because we think that women have a role to play, and people who are older have the means, the time, and the incentive to participate and protect the future of their grandchildren.
Yeah.
So if anybody wants to join her organization after races,
Grandfathers are welcome too.
one more, then we're going to take a quick
Dr. Somerville, on the, your silver buckshot.
Right.
What, can you theorize, I didn't notice it up there, if population growth, theoretically,
Yeah.
across the world, reached zero,
Yeah.
how would that affect?
Oh, that's very powerful. That's just a multiplier. I can talk about it because I'm not running for public office, but that's such a political hot potato, you can't talk about it. People start talking about genocide and so on. But in fact, the world right now has more than 7 billion people in it. It's still growing. And I sometimes have fun asking a class, when do you think it was 2 billion? And they say, well, I don't know, 500 BC. It was 1930. And so the population of the world has more than tripled in one human lifetime. Never happened before. We can hope will never happen again. But that's simply a multiplier. And this is at a time where women all over the world are saying they'd rather have fewer children. And
thank you, Jerry, for this very flattering introduction. And thank you for Richard for his very good review of some of the climate change issues, some of the main results from the IPCC report. In these next 45 minutes, I'm going to take a sort of a narrower view at the problems we're facing, just focusing on land ice, because this is what I study. You'll see that while major progresses have been done in studying especially the ice sheets in Greenland and Antarctica in the past 10, 15 years, there's also a lot of things that we don't know. Because a lot of the history of studying this ice sheet is fairly recent. To a lot of us, a place like Antarctica looks like a white continent with a sort of immutable character. This ice sheet has been here for thousands of years. It takes millennia to change its shape, to change snowfall on the ice sheet. And the traditional view, especially in the place of Antarctica, like Antarctica, is it's very remote. It's almost remote from the rest of the planet in terms of its climate. And it's very hard to imagine that this place is going to change, even during a human lifetime. And I think this view is still pretty much anchored in the mind of many scientists working in the field, to the point that when we see rapid changes happening in these places, it's a little bit shocking. It's a little bit something unexpected. But as you'll see in this animation, Antarctica is kind of a live place. This is an animation which shows the flow of the ice measured from satellites. This map was assembled just a few years ago. And it shows the ice that piles up in the Antarctic being channelized through these rivers, which we call glaciers and ice stream, towards the coastline. And you see that everything is moving in Antarctica. In fact, one of the challenges that we had in making this map was to use points which we knew didn't move, right? Because if you go in the wide interior of East Antarctica, all the ice is moving on a very different time scales. On some of these outlet glaciers, which are shown in purple here, the ice is moving at kilometers per year, but in the interior, you talk about centimeters per year, right? Which requires special techniques to measure. Is this a laser here? Oops. I did something wrong. Yeah, yeah, I got the laser. So this is Antarctica and Greenland. Antarctica is about 1.5 the US, 1.5 times the US. It's 7 times bigger than Greenland. We tend to focus a lot on these areas because they hold almost all the land ice in the world. I'm not going to talk too much about the glaciers in the mountainous regions of the Alps, Himalayas, Alaska, Canada, and elsewhere. Because the impact is very different. The impact of these glaciers, of course, is going to be significant on sea level in the coming century, but they're also going to have an impact on local populations in terms of water supply, local hydrology. Here we are interested in Greenland and Antarctica for 2 reasons. One is that they are the big gorillas in terms of sea level rise in the future. Antarctica holds the equivalent of 60 meters of global sea level rise, and Greenland about 7 meters, right, 20 feet of global sea level rise. If you melt all the ice in Greenland, you raise global sea level everywhere by 7 meters. And there are records from the past. This is relative sea level, and Richard mentioned that earlier, since the last glaciation, and we have a good record of how sea level changed with time by looking at coral records. And you see that sea level has changed by about 120 meters since the last glaciation. And the glaciation proceeded at some, you see that this curve is not smooth. There's some bumps and hollows in it. And we are towards the end of the curve here. Most of the deglaciation of the ice sheets is achieved. We don't have an ice sheet in northern Canada. We don't have ice sheets in Scandinavia. All of these ice sheets are gone. We're left with these 2 gorillas here, which still have enough to raise another 60 meters, 67 meters of sea level. As a glaciologist, I'm worried about these pulses, which actually are called meltwater pulses here, where sea level was not proceeding at the same pace as the long-term trend, but much faster, about 40 millimeters per year. Sea level at present is rising at 3 millimeters per year. So we know that there's periods in the past during the deglaciation history of the Earth where sea level was rising 10 times faster. And this is not due by the ocean, it's not due by mountain glaciers, it's caused by big ice sheets melting very rapidly into the ocean. This shows that an ice sheet like Greenland and Antarctica is unlikely to melt like a big block of ice slowly, because you're in a warmer climate. You know, you put the block of ice out of your fridge and you let it sit on the table, it's going to melt slowly with time. There's a lot of non-linearity in the system that make it so that this piece of ice is not just going to melt like your big ice cube from your fridge. It has its own dynamic, right? I showed you the flow of ice that is measured from satellites. Most of these rivers of ice control the discharge of the snowfall accumulated on the continent into the ocean. They're like taps disposed all around the side of the ice sheet. And these taps have their internal control. You can turn them on and off, depending on climate and depending also on the particular geometry of these glaciers. So these sorts of records suggest that during the glaciation history of ice sheets, there are periods where the ice sheets accelerated its decay. And the only way this can happen is if the ice is transported from the interior regions to the ocean much faster than usual. That means the glaciers are speeding up. And to have this level of sea level rise during this short period, that means that the glacier basically got crazy for a while. So as a glaciologist, we are of course concerned about the melting of Greenland and Antarctica as they are today, but there are big gorillas down the line where the potential for these ice sheets to decay 10 times faster exists, right? It's been done in the past. And we'd like to understand how this can happen. My talk will be, I apologize for that, a little bit going more into technical details, but I think I want you to understand also some of the things we know about the ice sheets and some of the things we don't know. This is a little cartoon that explains how an ice sheet forms. It forms from accumulation of snowfall that densifies into ice. And when ice is thick enough, about 100 meters, it starts deforming like a viscous fluid. And the ice is transported under deformation of its own weight towards the coastline. In Greenland, it reaches the ocean and breaks into icebergs. It interacts with the ocean. In Antarctica, in a colder climate, that continental ice is becoming afloat on the ocean and form what we call ice shelves, which also interact with the ocean and eventually break up into icebergs. Greenland and Antarctica, in terms of precipitation, are like deserts, right? You see the precipitation numbers for Greenland, 24 centimeters per year, 17 for Antarctica. The average precipitation on the Earth is 1 meter per year. Right? So even though there's a lot of ice in Greenland and Antarctica, it snows very little. In the Antarctic, it melts very little. In Greenland, you see that about half of that snowfall is melted and half is discharged as icebergs at the periphery. In the Antarctic, we have, of course, a much greater accumulation, not because it snows more, but because Antarctica is 7 times bigger than Greenland. We have no runoff. Most of the melt that occurs in the Antarctic refreezes in place. There's very little rivers of water flowing out of the Antarctic ice sheet as opposed to Greenland. So most of the ice is transported to the ocean and breaks into icebergs or melts into contact with the ocean. So these areas are very big. Surface parties, earlier explorers that tried to figure out what the ice sheet could do, whether it was growing or shrinking, had an enormous task at hand. Imagine surveying the continent 1.5 times the US, and you have to decide whether it's growing by a few millimeters up or down. And we give you a bunch of instruments to measure that, and a big paycheck, and lots of food, and ask you to come back when you have an answer. You may never come back. So to look at this vast extent of ice, we use satellites. And satellites have not been around for so long to do these measurements, right? You saw the record for the sea ice extent that Richard showed you. It started in 1978, these were the first satellites that could observe the polar regions. In 1978, the satellites were good to make images. They were not good to make very precise measurement, for instance, of the height of the ocean surface or the height of the ice sheet above sea level. It took some work for engineers to push the technology to where it is now. And now actually the technology is absolutely amazing, right? Because you can measure sea level. When we say sea level is rising by 3 millimeters per year, that means obviously that our noise level is much lower than that. Right? So we have a satellite up in the air at 800 kilometers that measures the height of the ocean surface and can tell you within fractions of millimeters what it's doing. I don't know how they do it, but they do it. So one way to measure the ice sheet is to do altimetry. So you're using radar or laser on board a satellite, and you're looking down, and you measure the surface of the ground, and you do that repeatedly to see if it changes with time. It started mostly in 1992. Before that, the satellites were not quite good enough to do that. So the record is 20 years. It's good, but as Richard showed you, when you're looking at climate signal, 20 years is still a short time. So there's batteries of satellites being used, and these future satellites are going to be used for that. In 2002, a new player came around. It's a mission that measures gravity. And gravity on the Earth is influenced by the distribution of mass at the surface of the Earth. They have, so it's actually 2 satellites that are about 200 kilometers apart that are flying around the Earth. And when they fly over different mass distribution, they have a different rate of acceleration. All right, so when they come close to a big mass, they tend to accelerate, and they move away, they slow down a little bit. So engineers have devised some devices that measure the distance between these two satellites as they move around the Earth. And from that, invert the data to figure out what the distribution of mass is on the Earth. Another amazing feast of technology. In the case of ice sheets, of course, if you can measure the change in gravity over time, you measure the change in mass of the ice sheet. You have a direct answer as to what's going on the ice sheet. Right? Here you measure, in a way, the height of your child as it grows. Here you have a scale. You measure how much they weigh, which is actually what we really want to know. Because the height of the child doesn't necessarily tell you about its density. You know? It can be a thin child or a thick child. Here we use a scale. And then the last method, which is probably a little bit more tricky because it involves a lot of information about the ice sheet before you get some numbers. It was the historical method that people used to figure out what glaciers in Greenland and Antarctica may be doing, whether they're growing or shrinking. It's what we call the mass budget method. So you look at what comes in and what comes out, and the difference tells you whether it's gaining or losing mass. The problem with this approach is that what comes in is a very big number, and what comes out is a very big number, and you're interested in the little difference between those two. So to look at what comes in, you have to measure snowfall all over the Antarctic. People have been doing that since the IGY. You drill a snow core, you measure the density of the snow, you can drill even deeper and look at an ice core and measure the rates of accumulation. You can easily imagine that you can only drill in so many places. If you want to capture the general pattern of accumulation around a place like Antarctica, it's going to take a lot of drilling. And of course, technology has evolved. The way people were looking at these records in 1957, when they were seriously considering whether they would not come back home or not, is a little bit different from what is being done today, where we can drill at 3 kilometers of ice. We have good information on what falls in the Antarctic ice sheet today, not from people going on the ground and measuring ice cores, but from climate models. Climate models that are constrained by what we call reanalysis data. We take all the climatic observations around the Earth and reinterpret them to reconstruct the climate state of the Earth. And models are using that to reconstruct the amount of snowfall on the Antarctic continent at a higher resolution. And these models have come a long way. When I started in glaciology, some of my esteemed colleagues were already pointing their nose saying, these models are going to become so good, you won't need to go on the ice sheet anymore to make these measurements. You only go on the ice sheet to verify that these models are reconstructing what happened back in the last year. I didn't quite believe it, but the first time I heard that, the person who said it was such a serious guy. It sent a big signal in my spine. I thought, if he's right, that's sort of amazing. We're all skeptical about models, but these models have really impressed me in the way they reconstruct the amount of snowfall and melt on the ice sheets using reanalysis data. So we have a good control on that from climate models constrained by climate reanalysis data. And along the periphery, we want to measure the outflow, and for that we're using satellite techniques, so we can measure the speed of the glaciers with satellites like I showed you. And then we need to measure how thick the ice is. And that we don't know how to do from satellites. It's using radars carried on airplanes, so you have to fly around the Antarctic continent to measure the thickness everywhere with airplanes. It can be done kind of easily in Greenland. In Antarctica, we haven't quite done that yet. There's a lot of places where it's very difficult to get to. So what are some of the things that people have seen since they started these measurements? And I sort of became involved in this research in the early 1990s. At that time, NASA decided to focus on the Greenland ice sheet to figure out whether it's growing or shrinking. Right? So they put a battery of instruments to look at that. But in 1990, we did not know whether Greenland was gaining or losing mass. We had absolutely no idea what was going on in Antarctica. No idea. The first instrument that was flown on the ice sheet was a laser altimeter to measure the height of the surface with time with very high precision. We have a noise level of about 10 centimeters. Right? We can measure from the aircraft the height of the surface and come back over time and see if it changed. This was extended later on by a satellite mission called ICESat. And what they found very early on is that there was a lot of mass loss along the periphery of the ice sheet, and the center of the ice sheet was just wobbling around, but pretty close to zero. And the new data confirmed also this pattern of mass loss along the ice sheet. And you see these red blobs correspond to areas that are going down faster than the rest. They correspond to these outlet glaciers, these areas that are colored in purple here where the ice is flowing fast. Right? So this was showing that the ice sheet was not changing only because it was melting more along the edges because of a warmer climate. The glaciers were doing something. The glaciers were actually responding in a very strong way and thinning, losing mass with time. How fast were they thinning? Well, I told you these lasers were designed to measure the height of the surface of Greenland within 10 centimeters in order to measure changes over the long term. On this scale here, we plotted some of the rates of changes in elevation in meters of the outlet glaciers of Greenland. You see the scale goes from 0 to 50 meters. We have a noise level of 10 centimeters with our lasers. I sometimes claim that we could have measured these changes in height of the glaciers just using a pot of paint on the side of the glacier, saying, it's here this year, let's come back in a couple of years, and we'll see a mark of paint up on the cliff. Right? These rates are astounding. 50 meters per year close to the edge of the glacier, 30 meters, 50 meters. Of course, some of them don't change too much, but these are very, very large rates. Some of these glaciers spin so rapidly. You see a picture here with this red arrow of Kagaklussuaq Glacier in East Greenland. There are some pieces of ice still attached on the side of the valley because the glaciers accelerated and thinned so rapidly that ice didn't have time to flow down. It just stayed attached on the side. Right? That's what we call a rapid drawdown of these glaciers. Jakobshavn Isberg is the biggest glacier in Greenland. It drains on its own about 10% of the whole island. It used to flow at 5 kilometers per year. It was one of the fastest moving glaciers in the world. It's been retreating. This is the Little Ice Age here, 1951. It's been retreating about this much in 50 years. Another equivalent distance here, which is about 10 kilometers in another 50 years. Another little bunch in another 50 years over here. And from 2001 to 2006, it retreated even more than the previous period. Right? All the flooding extension of this glacier is gone, and this is showing 2006, 2005, but the glacier keeps retreating here in this very deep channel. The glacier doubled its speed in 2002, and the flooding extension disappeared completely. That means the glacier now is ending in the ocean, and as soon as it reaches the ocean, it carves into these big icebergs. You can see the thinning of the ice measured from airplane. This is Jakobshavn Glacier. This is in red areas that are going down more than 15 meters per year. This is measurements collected between 1997 and 2002. And if you look at a few years later, you see that the thinning, the drawdown of the ice towards the ocean is extending farther inland. Now, we care a lot about this glacier because it's draining along a very deep canyon, just as deep as the Grand Canyon. So as it retreats it inland, the ocean follows the glaciers inland, and glaciologists have known for quite a while this is a configuration that is prone to instability. So a lot of us are worried that this glacier, Jakob Savvatisbury, it's on a path of retreat right now, and it's going to be very difficult for that retreat to stop, because it's in a geometry configuration that is such that there's nothing that's going to make it stop easily. But Jakobshavn is not the only glacier in Greenland. This is a little bit of a complex map, but we saw glaciers speeding up in the southeast. Jakobshavn is here in this part of Greenland. Then some glaciers started accelerating in the central east. And then a lot of glaciers accelerated also in the northwest in more recent years. There's a few glaciers that slowed down. I think all the red arrows are areas where there's big speed up. This glacier slowed down, and this one, and this one. We really have to search for them to find them. There's a few that slowed down. Antarctica, this is also a result from satellite altimetry. So the areas that you see in red here are going down very fast. The areas that are colored blue are going up. And here we don't have data. So we call this part of Antarctica East Antarctica because it rests on a higher plateau. In fact, if you work on the East Antarctic plateau, you're doing high altitude work, right? The plateau is at high elevation. The air is much thinner in the Antarctic than it is at our latitudes. You can get a little bit sick when you work in this area. So we call this the plateau, the East Antarctic plateau, and this is West Antarctica, which rests on a bedrock that's below sea level. So all these glaciers and ice sheets here are glaciers and ice sheets that are almost afloat in the ocean. They want to be afloat in the ocean. So there's a large area of mass loss here, which is in the Amundsen Sea. There's some losses along the peninsula, that part of Antarctica that sticks out towards South America. Not much elsewhere except this very important area here, which is called Totem Glacier in East Antarctica, which people are looking at more and more these days. This area has an equivalent of about 7 meters global sea level rise, and has been the focus of a lot of studies because it's suggested to be unstable. If there's a part of Antarctica that's more likely to collapse, it's this one, West Antarctica. But this area here, C prime D with Totem Glacier that seems to be going down, holds just as much ice as the whole West Antarctic continent. If it were going down to sea and collapse, it would raise global sea level by another 7 meters. These are the type of change we see in the Amundsen Sea. This is Pine Island Glacier. It has a few other glaciers nearby. These are some measurements we collect from satellites. And we see this glacier accelerating, and we see the acceleration of ice expanding very far inland. In fact, if you imagine that this is the drainage basin of this glacier, right, and this is the flow of ice from the flank of the basin into the main trough here. When we see the glacier accelerating here, we can see the effect of the acceleration almost all the way to what we call the ice divides. Right? So that means that there's something going on along the edges of the ice sheet that affect the glacier stability, and it's transmitted very far, hundreds of kilometers inland, almost instantaneously by the ice. So what's happening over here several hundred kilometers away from the coastline is not independent from the coastline. Right? There's some connection pathways between these two. In 2002, the Larsen B ice shelf collapsed, and that made it in Hollywood movies. What was that movie? The Day After Tomorrow? Right. And you have these glaciologists that fall into a crack and hang up with one ice axe. Yeah, right. Yeah, right. This was just a series of collapse of ice shelves in the peninsula. This one struck a different chord on us because we had satellites to look at it almost real time and go, wow, Right? That's floating extension of ice had been retreating slowly over time, but in March 2002, we saw the whole floating section splatter in a bunch of icebergs in just a period of 3 weeks, like a domino effect. And what was particularly interesting was to look at the effect of this floating ice on the glaciers that flow into them. Right? 40 years ago, the early glaciologists, the early explorers, right, which I learned to respect a lot, because even though they were the early guys starting a new field with very little data, they were very clever guys. A lot of them were extremely clever. And they realized very early on that if you remove this floating extension in front of the glaciers should speed up a lot. Some more advanced people, maybe with fancier models, came along and disputed that idea and said, well, we have more fancy models now, and we don't actually think it's true. Their models were way too simplistic, and my new model, which has more complex physics and more complex geometry, says it doesn't matter. So we had a reality check with Larsen B to figure out, with these glaciers that used to flow in this ice shelf, are they going to speed up or not respond? Well, they used to flow at about 300 meters per year before the collapse, and they started flowing at 1,500, 2,000, 2,500 meters per year. So did they still speed up? Yes. A little bit? Oh no. By a factor 3 to 8. And this was not a part of Antarctica that people considered to be particularly vulnerable to this kind of instability. These glaciers are not the typical glaciers that we think are unstable elements of the Antarctic ice sheet. The first reality check we have with the collapse of ice shelves and the influence on glaciers said, well, they changed in a very big way. And those early glaciologists were damn right that this is very important. To put this in perspective, if all the ice shelves around Antarctica were to do this, and all the glaciers were to speed up by a factor 10, somebody already did the calculation. We get 2 meters sea level rise by the end of the century. So it happened already in the Antarctic. This is a little movie of the mass loss in Greenland from GRACE. So GRACE is this fantastic data now that we can use almost like the Weather Channel to see what the mass of the ice sheet is doing, except the Weather Channel looks like it's a bit stuck here. I'm sorry, I'm going to see if I can. Well, it used to work on my computer.
That is your computer.
It is my computer. Okay, that's all right. Anyway, GRACE acquires data every month globally. So now we have the Weather Channel. Or it's not really the Weather Channel. It's a scale that works continuously, that shows us almost in real time. Every month we have a new data point on the Antarctic or the Greenland sheet to see how the mass loss is evolving. So what this movie was going to show you is the growth of the mass loss in this area of West Antarctica and the peninsula, and a little bit of blob starting in East Antarctica. Okay, I don't know how I'm doing with time, but I'm not doing so great. This is a little bit of a complicated plot. I apologize for that, but this is showing the mass loss of the ice sheets with time, measured since 1992. In red are the GRACE data, and in black are the mass budget method data. Okay, so this is the mass loss in gigatons per year. So 250 gigatons, more or less, for the Greenland ice sheet. That's very small compared to the volume of ice in Greenland. It's not small compared to the annual precipitation on the Greenland continent. It's about half of it. On the human scale, I used this analogy before, 1 gigaton of water is the consumption of the city of Los Angeles every year in fresh water. Right? So the amount of water that Greenland is losing, it's small compared to the reserve of water in Greenland, but compared to a human being, there's enough water here lost by the Greenland ice sheet to feed 250 cities like Los Angeles every year with all their supply of fresh water. So it's a small leak compared to Greenland, but it's a big leak compared to our consumption of fresh water. You see that the mass loss is increasing with time. Right? So it's not like Greenland is melting at a steady rate. It's melting more every year. The glaciers are losing more mass every year. You do see a lot of variability in that signal, and Richard mentioned that to you earlier. When you look at long-term trends in temperature, you can take some shorter time periods and find any signal you want. You can say Greenland is growing or shrinking on very short time periods. It doesn't mean anything in the long term. But if you look at these 20 years of data, there's a pretty nice indication of an increasing mass loss. In Antarctica, the fluctuations are even bigger because it's a big place, big amount of snowfall. Everything is bigger in Antarctica. Right? It's like when you're in Europe and you move to America, everything is bigger in America. Right? This is Europe and this is America. But in Antarctica as well, you see an increase in mass loss with time, and this is the two ice sheets combined together. So the first thing that we get of these measurements is that when we look back in the 1990s, these ice sheets are losing more mass than anyone expected at the time. And the increase in mass loss per year is also something no one in the scientific community thought of. I would push things a little bit farther and say, well, let's look at this trend here, how much these ice sheets are starting to lose mass since the 1990s. And let's assume they keep going at the same rate for many decades. Let's push it all the way to 2100. How much sea level rise would we get? Well, we get, combined with the thermal expansion from the ocean, we get about 1.2 meters. So a few years ago, when we were talking about the sea level rise of 1 meter in 2100, a lot of eyebrows were raising. Now it's a little bit more an accepted possibility. All I'm saying here is that it's certainly not science fiction for ice sheets to do that. They are on a pace of losing mass right now, and that pace says if I continue at that pace, I'm going to get to 1 meter sea level rise by the end of the century. We are already doing that. Of course, there's a danger in extrapolating because, as I showed you in the first view graph, ice sheets are non-linear. Right? So they could slow down their melting rate. They could also speed it up. That's the big question. That's the multi-million-dollar question. How much time do I have, Jared?
10 minutes?
10 minutes. This is the biggie, and the story is not done yet. These are the projections for sea level in the 21st century. So sea level is rising for a variety of reasons. Right? One that we understand pretty well is thermal expansion from the ocean. The ocean gets warmer, it expands, and sea level is rising. There's some fluctuations in water storage on land. There's some fluctuations associated with the melting of mountain glaciers. But down the line, the dominant contribution to sea level is going to be whether the ice sheets are melting or not. I told you, 67 meters of sea level rise if they both go down to sea. So there's a lot of studies being done to predict what sea level rise is going to be by 2100. Danger number one, the world doesn't end in 2100. Right? Although you can find Maya predictions that are going to say that. And for sure, sea level is not going to stop rising at 2100. In fact, one of the most shocking revelations about sea level rise is that it's going to go on for centuries to come, no matter what we do today. The question is how fast it's going to rise. The last IPCC AR4 had projection of about 40 centimeters sea level rise by 2100, but they noted that there is some uncertainty about the role of ice sheets in there because we don't have good models to predict what ice sheets are going to do. So let's assume it's 0. That's essentially what IPCC-AR4 had to do. Stefan Ramsdorff published a very simple model in about the same time the IPCC report came out, which correlates sea level with temperature. Just on the simple fact that when the climate is warm, sea level is up. When the climate is cold, sea level is down. There's long-term records that show that this is a very strong physical connection between the two. It's another thing to make that connection on shorter time scale, and especially over the time scale of a century. So there's a lot of uncertainty about that. But what came out of this simple model is a projection for sea level that was much bigger than IPCC, right? About 1 meter. So this means that the difference is either caused by ice sheets that are not modeled properly by IPCC, or the model used by Stefan Ramsdorff is wrong. Right? Fortunately, as it happens in science, when somebody comes for a breakthrough, a lot of other people come in and try to do it again, or try to tweak different numbers. And there's been a lot of studies with these empirical models, different ways to do the calibration. And the numbers haven't changed that much compared to what Stefan published in 2006. And they still stand a little bit higher from the IPCC projection, which admittedly don't do a good job with ice sheets because we don't know how to predict what ice sheets are going to do. I have a personal problem with that. I've become personal here. I don't like these IPCC projections very much because they neglect what's happening in ice sheets. And it can't be zero. It's not zero today. There's no reason for it to be zero tomorrow, even less. I'm worried about Stefan Ramsdorff's model saying it's going to be about 1.2 meters. He might be right, right? So if I am the Prime Minister of Holland, who do you think I'm going to listen to? The low projection of 40 centimeters, or I'm going to build barriers around the country that, in case Stefan is right, maybe we should prepare for 1.2 meter sea level rise. The dilemma here for politicians is that if they need to get ready for 1 meter sea level rise, they can do that just in the snap of a finger. Right? It's going to take a long time to build these structures, and they're going to have to last at least 40, 50 years. So if you want to get ready for 2100 and you're the Prime Minister of Holland, you're thinking right now about what you need to build for 2100. You can't tell your citizens, I'm going to build it, it's going to be okay until 2080, and after that, I'm not sure. Because 1 centimeter too low is just not good enough. And I plugged in this number here, which some of my colleagues don't like at all. They don't think this is reasonable. But a lot of people do that in science. They look at trends over 20, 30 years and they say, what if it continues for another few decades? What do you get? Well, if the present trend continues, we get about here, so close to the Ramsdorff model. What's happening in terms of the climate? Greenland is warming, right? And in fact, it's warming. The melt area is increasing. I don't know if you heard, but in 2012 was a record year in Greenland. The whole ice sheet melted. So this is 2007. All the areas in red melted. In 2012, the whole island was red for the first time in 150 years. It is warming in Greenland. This is result from the Swiss camp. So they have Swiss thermometers. The PI is a Swiss guy. You can trust Swiss technology, right? You can see the scale here, about 4 degrees since 1991, 4 degrees warming, 2 degrees by decade. So much more rapid than the global average. The numbers that Richard showed you are global average, right? And we know that in the polar regions, climate is warming faster. How much faster? Well, try twice faster, maybe 3 times faster. Precipitation in blue here hasn't changed very much. There's a lot of talks about precipitation increasing in the ice sheets. We haven't quite seen that yet, but we've seen a very large increase in the melting of the ice since the 1980s, 1990s. In Antarctica, things are much more difficult because there's not a very long record of measurements. So what do we know? We know that from the reconstruction of snowfall There's a lot of fluctuations with time, but there's not any expression of a long-term trend. We don't see a growth of Antarctica predicted by models in a warmer climate. We don't see an increase in snowfall in the Antarctic continent. There's indication that the Southern Ocean is warming. Right? This is a paper by Sarah Gill from Scripps. And you notice that there's a lot of white areas around the Antarctic continent. Unfortunately, we don't have data there because there's sea ice cover. So we don't know exactly what the ocean is doing there, but there's indications that the Southern Ocean is warming. And there's a lot of literature, including papers published last month, looking at temperature record in Antarctica. And there's indications of warming, but there's not a broad consensus on what's happening on the Antarctic because the instrumental record is a little bit difficult to look at. You perhaps heard about a lot of research done to look at the effect of meltwater on the flow of ice. Right? This meltwater makes it down the bottom of the ice sheet through moulins or crevasses. It helps lubricate the bottom of the ice and helps the ice flow faster. Right? A lot of research has been done on that. And what came out of that is that it's not a big factor in driving glacier retreat in Greenland or Antarctica at present. In fact, there are even results that suggest that it doesn't help at all the ice to move faster. What happens when this water connects to the bed? It's raising the pressure underneath the bed. You pile some water at the bottom of the ice sheet, raises the pressure, lifts up the ice, and allows the ice to flow faster. But we have a complex plumbing system underneath the ice sheet. All these little channels of water are connected, eventually become connected. And at some point, when they're all connected to the sea, the pressure is released and the ice sheet rests again on the bedrock. So basically, when you put a lot of meltwater at the surface of the ice sheet, you can get a little bit of speed up of the ice, but it's not going to last very long. And in fact, some studies have shown that if you put even more water, there's going to be a big speed up, but it's going to be even shorter. So overall, the impact on the all flow of the ice sheet is very small. So to cut the story short, the meltwater is not really central to what's happening to the Greenland glaciers. And of course, what's happening to the Greenland glaciers is something we didn't think about. Now it sounds like very obvious, but we didn't think about that at the time. All these glaciers terminate in the ocean. And for some reason, glaciologists, when they talk about interactions of glaciers and ocean, they talk about freezing of ice in the ocean. And oceanographers, they always talk about ice melting in the ocean. I think there's something very profound about that in human nature, that glaciologists can't accept that maybe their ice is melting in the ocean and becomes water. But all these glaciers terminate in the ocean, and they interact very vigorously with these ocean waters. And the ocean is part of the climate system, right? We think a lot about what we can see at the surface of the ice sheet, which is air temperature. It's a little bit more difficult to think conceptually about what's happening below, at the base of the ice sheets, or in the submerged part of the glaciers when they reach the ocean, where they interact a lot with the ocean. And you can't see that because it occurs hundreds of meters or kilometers below the surface. Well, we think that, I have to skip a little bit more on this. We think this is a big factor in Greenland and Antarctica. In Greenland, this was shown by a colleague, David Holland, in 2008, looking at temperature records along the coast of Greenland. These temperature records are not based from scientific stations. They're based on ships, fishery ships that are fishing for shrimps, and they collect data about the subsurface temperature. That's the only data set he could find that would give an indication of what happened along the coastal waters of Greenland. And he found that about 1996, 1997, a lot of warm waters appeared along the coast of Greenland, just at the same time as a lot of these glaciers started to speed up. These warm waters are of subtropical origin. They come from the Northern Atlantic, and they're drifting along the coast of Greenland here in the Heminger Sea. Most of these waters are not at the surface. These warm waters are not at the surface. They're about 300–400 meters below the surface. You can't even see that from satellites. That's where remote sensing becomes a little bit challenging. We're starting looking at stuff that we can't see from the surface. 400 meters below the surface, Greenland waters are warm and they melt the ice. And at the surface, they're cold. And we have a similar thing going on in the Southern Ocean. There's also a lot of warm water that's at depth. I have to skip that for the sake of time. Apologize. Okay, there's one more view graph. So in the Antarctic, where do we find warm water? We find warm water, that's not the only way you can melt the ice, but warm water is around circumpolar deep water along the Antarctic circumpolar current. And there's some parts of Antarctica where this water comes close to the Antarctic continent, like right here, which is exactly where we see a lot of mass loss of the ice sheet. And there's evidence that this warm water is able to intrude onto the continental shelf and reach the glaciers and melt them faster than they should. And if they melt faster, they tend to flow faster. In Greenland, the source of warm water are from the northern Atlantic. Right? This is the Gulf Stream. Part of the Gulf Stream goes along the coast of Norway. This is why you can grow strawberries in Norway, but you can't grow strawberries in Greenland. And part of it is deflected here along the Immigrant Sea, along Greenland, goes back into the Labrador Sea. Some of it goes into Baffin Bay. When these warm waters reach the glaciers, they trigger glacier acceleration like we've seen in the last 10 to 20 years. Some of the problems we face, if we want to understand how this ocean heat is able to reach the glaciers, we have to understand very well what the seafloor topography looks like. We have amazing data about the global seafloor topography. But when it comes to ice sheets, as you come closer to the ice sheet, you get less and less data to the point where there's actually no data, right? This is the coast of Greenland with all the ship tracks ever collected seafloor bathymetry data. Notice this area here along the coast of northwest Greenland. There's not a single data point for measurements of the seafloor topography. So if we know that there's warm water in Baffin Bay, we have no ways using conceptual model or numerical model to tell you if this warm water can or cannot reach the glaciers. So I'm spending a little bit of my time now doing oceanography, probably in anticipation that the ice sheets are going to melt down anyway. But because glaciologists really need to get their feet wet nowadays, if they want to understand what's happening to the glaciers, they really need to understand what's happening to the ocean. And to understand what's happening to the ocean, we need to understand the wind and the atmosphere. It's all connected. But glaciology has proceeded a lot in its own universe of ice, and we realize now that it's a much more complex machinery. So we collect bathymetry data, and we have a lot of fun collecting bathymetry data in the fjords of Greenland, because everywhere we collect data, we are the first one to collect it, and we are in 2012. Right? How cool is that? In 2012, you can still explore places and make measurements that nobody has ever made. Right? And in the fjords of Greenland, this is the maps, the global seafloor topography map from Smith and Sandwell, using all the available data. We have fjords that are about 250 meters deep. At that depth, warm water can't intrude the fjords. You can't change anything on the Greenland glaciers with a topography like this one. When we collect measurements, we found the fjord's depth to reach 1,500 meters over here. In the main part of this trough here, it's more than a kilometer below sea level. Warm water has absolutely no problem reaching these glaciers if it's present outside on the continental shelf. But that's not the end of the story. I'm just telling you we don't know the bathymetry around these ice sheets very well. When we come, I want to show another view graph. I'm not going to show the bathymetry. When we come to the ice sheet, we have some problems with the existing data as well. This is a map of the bedrock beneath Greenland. So if you were to remove the ice sheet completely and not let the crust rebound because of the big weight of the ice that's gone away, it would look like this. And all the blue areas would be below sea level. And some of these troughs here are occupied by very big glaciers that drain ice from the interior. So it's important for us to know the areas that are below sea level because these are more prone to rapid retreat. It's also important for us to know the connection along these channels that are below sea level. And we have a long way to go. This is a map of the bedrock beneath this glacier here. I forget the name of this glacier, Northwest Greenland, as we knew it in 2001. Almost nothing here is below sea level. You can't even see the trough where the glacier is flowing. A lot of data were acquired by NASA on airplanes, and we reconstructed a map like this one. And you kind of sort of guess of it, some channels here that are reaching through the bedrock. And this is a newer map which combines measurement of thickness and measurements of ice motion, where we reconstruct the bed by saying mass needs to be conserved along the way. And now we're seeing these big channels appear, big, deep below sea level, and very far inland. So if you're an ice sheet modeler, right, and you're using this description of the topography of Greenland, do you think it's going to be easy to find a big influence of the ocean on these glaciers? Do you think it's going to be easy to make these glaciers retreat fast when there's no channel, no freeway for them to retreat fast, as opposed to a landscape like this one, where a lot of these glaciers are just ready to go? You just need to push them a little bit. They are probably anchored in an old seal on a little bump, and they don't need much to be pushed and start moving backwards, 50, 100 kilometers, maybe 200 kilometers inland. That part of the ice sheet is what matters for us in the next century. Not so much what's happening 1,000 kilometers away, but this is the part of the ice sheet that's going to change. This map is just a month old. This is where we are now, unfortunately. So it's kind of a race against time to get the story right on the ice sheets. Another example of that is if we couple the existing bathymetry with the topography that I just showed you. The existing topography says just before we reach the glacier, there's a big wall here that raises above sea level. Right? And when you put the actual topography in there, you see a channel that's much more distinct and connects the ocean with the land ice. So we have a lot more to do collecting this basic data. And I have another movie here, which may or may not work, of the flow in Greenland. And I'll stop here.
All right, thank you. As you said, at the present, these were two statements, this and the following one from Somerville. Warming of the climate system is unequivocal, as is now evident from observations of increases in global average air and ocean temperatures, widespread melting of snow and ice, and rising global average sea level. And remember, the IPCC can't put anything into a report unless it is signed off by all of the nations. So these are very conservative statements. Most of the observed increase in global average temperatures in the mid-20th century is very likely, probability of 90% or more, due to the observed increase in anthropogenic greenhouse gas concentrations. And remember, this was a very important graph. The challenge is to stabilize the levels of CO2 in the atmosphere, and then to have those decline over time. And in order to do that, the only way you can do it is to decrease the emissions over time. And that's no small challenge. Remember these three famous curves? The important points are the area under each of these three curves. The area is the same, and each of these has a probability of 2/3, 0.67, of keeping us within a 2 degrees Celsius, a 3.6 degree Fahrenheit increase in temperature over the pre-industrial. And later, this is if you stabilized it in 2011, well, we've already gone past 2011, or if you did it in 2015. If you did it in 2015, you have to reduce emissions 5.3% per year. So far, we haven't reduced emissions globally in any year. And if you wait till 2020, 9% per year. And most people, most scientists believe we've already gone past the 2 Celsius increase, and it's a question of, is it going to be 4 or 5 degrees? And even to achieve 4 or 5 degree increase. Remember, those are global increases. And that means that in some areas, it'll be significantly more than that. And as Somerville pointed out, 2 degrees is an arbitrary societal decision, doesn't have anything to do with science. Once you decide on what that number should be, then science can tell you how much you have to reduce emissions to get there. That's where the science comes in. Now, it's a little bit of an exaggeration to say there's no science. Many biologists who study biodiversity, and you'll hear one in our next class, will argue that if we get much above 2 degrees Celsius, we'll begin to see large changes in the distribution of ecosystems. And remember, this is what the carbon emissions are and how they're allocated among coal, oil, gas, and the cement industry. So coal and oil really are the big offenders. Gas is pretty good. And if you want to cut the emissions in half, these were some of the things that you could do. So these are the emissions. If you want to cut it in half, you could do it through these wedges. Reduce energy through electricity through efficiency, reduce non-electrical energy through efficiency, increase passenger vehicle efficiency, expand efficiency in heavy trucks and airplanes, expand renewable energy use, and capture and store CO2 at the source. And if you look now, so it's very clear that the only way out of this mess is to reduce CO2 emissions. We're going to come up with our 10-point plan this class. And your assignment is that by, not this Friday, but by a week from Friday, you have to email to Adina at least 3 and no more than 5 actions you would recommend be on the list. And before our class, we'll find which ones are in common, and then we're going to vote on these. And as I said, we won't put anything on the list that doesn't have a 2/3 majority. But let's see if we can do better than Congress and come up with some things that make sense.
We come up with one plan over here.
I'm going to put up some of the things that if I were czar, I would do. We're not going to discuss them because, frankly, I don't care if you agree with me or not. but we're going to do this in a very democratic way. But if I were czar, I would launch a massive public education programs, billboards, wrapped house, buses, TV weather reports, because I still don't think most people in the public understand the implications of all of this. I would set ambitious conservation requirements for all new and renovated buildings and offer incentives for older buildings. I would have even more ambitious standards for vehicle fleet average fuel efficiency. And I would promote the use of natural gas at power plants instead of coal as a transition, because I don't believe for 1 minute that we're not going to be going through this transition for a number of decades. And gas is cheap and it's available. And if you look at the United States last year, for the first time, our emissions would have fallen below had we signed the protocol. And it was only because utilities switched from coal to gas. And I would do it as a transition. I would at least maintain the present position of nuclear energy in the nation's energy portfolio as a transition for a number of decades. It's somewhere around 15% now in the United States and in California, although with San Onofre offline. Bob, what percentage of California is it now?
It was 19 to 20 before San Onofre went off. There's the 2 big plants. I presume it's probably 10 because Diablo Canyon still works.
So it's about 10.
I would guess.
And nationwide, it's around 15, 16%. And finally, I would double the investment in competitive research on governmental research in renewables and carbon capture every year for the next 5 years, and I would stabilize it at that level. We make a pitiful investment in renewables, in energy research. We talk about having a national policy for this. We don't have a national policy. Now, you don't have to agree with any of mine, but if you don't submit 3 to 5 by a week from Friday, because you have to submit them by email, so we know who you are. And if you don't get to vote. Plus, we'll put a list of the people up who are poor citizens. So our next class is not next week, but it's the following week. And it'll be a very interesting presentation by Glenn McDonald on how does the biosphere respond to all this? What changes are we seeing in the distribution, the diversity, and the abundance of life? Thank you all for coming. We'll see you in a couple of weeks. And don't forget to send in your